So we're going to continue with our frames and machines topic. And what I thought we'd do is we're just going to work two longer frames and machine problems. So this one is, they're both frames actually, this one and this one. We should probably do this one first. It's simpler than that one, but it does have some issues that we need to figure out how to deal with. So maybe copy that down if you want to, but basically you've got this little two-piece frame. There's a pulley of some kind. Again, in this course, all the pulleys are frictionless, so we don't have to worry about how the rope or cable or whatever around the pulley is interacting with the pulley itself. So that normally does make a difference, as the friction of the rope on the pulley itself and the pulley on its bearings and that kind of thing. But we're ignoring all that. The thing with this one is that there are no two force members, so I guess I should put some letters on here so we can talk about the different pieces. But let's call this one A, and then B, C, D. We'll call this point E since it is there. So each of these has more than two things connected to it. Also, A and B are both pins, which is not normal for our setup. Normally we had a pin and a roller. So this one has some issues that we might have to work on. But if we look up the total number of unknowns, we've got 2 at A, 2 at B, 2 at C, and that's it. So there's only 6 unknown things. E is just the cable. Whatever's going on at D is just by the cable because there's no friction. And so we only have 6 unknowns, and we have more than 6 equations to work with by the time we write free body diagrams and their equations for each of these two pieces. So we should have enough information to deal with, but we may not can start this one exactly the same way as we've started others by just solving for the external reactions, because there are 4 external reactions. There's no two force members, so there's not a way we can simplify one of these pins to just be a force at some known angle. So we're going to start with drawing a free body diagram of our whole little structure here. Actually, let's start with changing our 100 kilogram weight into some kind of Newton force. So again, web work usually, and I don't know if it always does, but it usually uses 9.81 meters per second squared for acceleration due to gravity when you're converting kilograms to newtons, but there might be instances where it uses 9.8. And web work is finicky enough that might make a difference in your answer, the 0.01 difference between those two. I'm going to use 9.8 just to make it simple. So we're going to take our 100 kilograms times 9.8 meters per second squared to give us a kilogram meter per second squared, which is a Newton. So we'll have 980 newtons. So now we actually have a force and not a mass that we're dealing with. So that'll be the first thing. Now we can go in, create a free body diagram of this thing. I think, I made this a picture, so I can't do that. Let's redraw the whole thing. So we have member BCD. There's the pulley over here at D. B, and I'll see if I can get both of them on the screen at the same time. There we go. C. So at B, we're going to have, it's a pin. So we're going to put BX and BY. Over at D, I'm just going to replace the cable with 980 newtons. And then we've got to draw this member AEC, and it kind of does something like this. At A, again, A is a pin, so we're going to have to put AX and AY. Sometimes you have a pin connected to a two-force member, and instead of writing the X and Y components, you can write just the force in that member at whatever angle the line of action is at. In this case, it's not an AEC, since it has 3 connection things. is not a 2/4 member. So we're going to make it just AX and AY. And I'm just going to draw them in positive X and Y directions, knowing that some of them have to be going the other way, but we'll draw them this way. And then at E, for now, I'm going to leave that connected to the roller. So I've got the information. Let's put some units on there though. So it said that this was 2.5. I guess these are meters. And this is also 2.5 meters. And then I had a piece of information about the pulley. It said it had a 1 meter diameter. So this is a giant pulley. That's probably too big. Let's make that smaller. Let's make that maybe a 1/2 meter diameter. So let's cancel that. Let's make this thing smaller so it's not gigantic. And this little symbol is telling us that's the diameter of that pulley, not the radius. So now we've got a free body diagram. We do need the distance between A and B. That's 2 meters. So it's not drawn to scale necessarily. It's close. And if we wanted to finish it off, we could put an x-axis and a y-axis here. All right, so got a free body diagram of the little contraption. And we want to start by, we've got 4 unknowns that we can look at. So we can solve some of these. We can get a value for AX and BX, I think, but we can't get a value for AY and BY that I can see. So let's take this free body diagram and do summation of moments about A. Might as well do A. Make that clockwise positive moments. Actually, if we, oh yeah, this will work good. So 980 newtons, that's the weight that was hanging off of the cable that we converted into a force. And that is 5.25 meters from point A. So the distance between this line of action and point A should be 5.25 meters. And then I've got, that's going clockwise, so I gave it a positive sign. Going counterclockwise, I have BX, and it's just 2 meters. So we should be able to solve for BX. Let's see. 980 times 5.25 divided by 2, 2,572.5 newtons. Okay, then we could do something, we could either do moments about B, or even easier, we could do summation of forces in X, and that will show us that AX plus BX equals 0, the way I drew it on the diagram, and that would show us that AX plus 2572.5 newtons equals 0, so therefore AX must equal a negative 2572. 72. Okay, and the negative sign there just means that AX really should be pointing to the left. And there's not an equation, there's not a moment or summation of forces in Y that I can use to find both AY and BY. I can determine that the summation of AY and BY is equal to 980 newtons, but that's it. So at this point, sometimes you get here and you can't get the rest of the external reactions, or like if it was a machine, then a lot of times you can't get any of the external reactions to start with. So what you do is you need to generate new equations, and you generate new equations by drawing new free body diagrams. So we can choose, remember, I forgot this letter. This is, let's see, E and C. So we can choose, remember, AEC or BC, this was D over here, BCD, and draw their free body diagrams. Maybe we should draw both of them. Let's just draw both of them. So this is AEC, At A, we already have one thing. We know that AX is supposed to go this way, and it's supposed to be 2572.5 newtons. We don't know AY. E, we do know. E is the cable wrapping around the pulley. It should be horizontal. It looks kind of like it's sloped. It's going to be horizontal. That cable is. So we know that E should be 980 newtons because there's not a frictional force acting on the pulley and the rope. So whatever force is on one part of that cable is the same force on any other part of that cable. So we know that we have 980 newtons at E just going out this way. And then at C, we don't really know anything. It's just a pin, so we'll put CX and CY on there. We can put some dimensions, but for right now, let's just draw the free body diagrams and see which one we want to work with. The other one looks kind of like this. You have, this was point B, and then we have C, and then we had D over here. B, we found BX was 2572.5 newtons. We never found BY, so we'll leave it unknown. I did already assign positive and negative directions for CX and CY when I drew the diagonal piece. So I have to use those same magnitudes, CX and CY, but opposite directions, the reactions to them. So on this piece, I have to draw CX going this way so that it's the opposite direction, and I have to draw CY going down. If I don't do that, then my free body diagrams aren't consistent with each other, and even though I can calculate some numbers, I won't get, it'll create a chain reaction of problems that eventually could lead me to calculate some incorrect numbers because one of the forces is going the wrong way. So I have to keep the magnitudes the same. In this case, the magnitudes are just variable names, and then the reactions opposite of one another on each piece. D, I did not draw the pulley at D. You could draw the pulley and draw the ropes around it and use those 980 Newton forces in the ropes, but since I am not dealing with friction on the pulley or on the bearing that the pulley is supported by, the bearing is the little, whatever surface, it could just be a hole or it could be roller bearings or whatever inside there that's allowing the pulley to turn. Since I'm not worried about friction there, I can take those forces, 980 newtons coming off horizontally and vertically, and I can put them directly on the pin at D instead of the pulley at D. So I can do this. I can go and put 980 newtons here and 980 newtons here. This is the same thing as if I were to do, here's the pulley. I'm going to draw it bigger just so we can see it. Well, let's do a circle. All right, there's a pulley, and oh, I have to do it every time. There. So this can be our pulley at D. So we know that, let's draw some of the rope so there's some of the rope coming off, and there's some of the rope coming off. And we know that we would certainly be able to do this, 980 newtons, 980 newtons. But for this pulley to be a free body diagram that's in equilibrium, I also need 980 newtons here and 980 newtons here. So those 980, the smaller ones, the ones on the inside, those are the reactions that are keeping this pulley stationary, right? Something has to keep it from just sliding to the left or up or down or something like that. And so those are the reactions. So what I drew here, these are actually reactions to these two guys. So that's how I'm getting from the 980 newtons in the ropes down to not just showing those 980 newtons right on the point D itself. And you can do that no matter what the angles are. They don't have to be horizontal and vertical, just whatever angle as long as there's no friction involved that I'm having to account for, then I can just take as if the ropes themselves, the cables were put right at D, and I can translate those forces using this idea. You don't have to go draw the pulley diagram and everything to make it valid. You can just take the forces in the cables and put them right at D. So that's what we're doing there. And why I can put the 980. Why would I want to put the 980 at D versus the 980 up a little bit? The reason I might want to do that is it just makes summation of moments a little bit simpler, right? Because now that 980 Newton horizontal force is going to go through any point B, C, or D. It won't create a moment about there. So it just makes the equation a little bit easier. I could certainly do 980 times the radius of the pulley and create a moment also, but it makes it a little bit simpler to do it this way. So if I look at our two free body diagrams, not the pulley one, that one's just kind of, it doesn't actually give us any new information, right? There's no unknown variables there. So these two free body diagrams, on the first one, the diagonal one, I only have three. I have three unknowns, AY, CX, and CY. So three unknowns, one free body diagram. I should be able to solve for all three of those. BCD, I have three unknowns, a different three unknowns, BY instead of AY, but then CX and CY are common between the two of them. So I should be able to use either free body diagram to solve for all three unknowns on that free body diagram. Then once I figure out those, I can go back to this guy and figure out the one I'm missing, because I'll either be missing AY or BY. Personally, I'm going to want to do, remember, BCD because it's nice and horizontal. I don't have to worry with angles and figuring out where things are located. It's pretty straightforward. Now, I didn't draw it apparently to scale because the way I labeled this, the distance from B to C should be the same as the distance from C to D, but that's okay. We will just label it that way, even though it's not drawn that way. So this distance is supposed to also be 2.5 meters. Get rid of that. So those reactions. So that looks like a pretty simple thing to deal with. So let's use that free body diagram, so that one, and write some equations associated with it. So if we do forces in X, that looks like there's only one unknown in X. That looks like a good one to do. Summation of forces in X equals 0 will tell me that 2572.5, that was BX, newtons, minus CX, minus 980 newtons should add to 0. So that'll let me solve for CX. And I'll have to get my calculator. 2572.5 minus 980, that's a positive 1592, but then I'm going to move it to the other side of the equal sign so it becomes negative 1592, and I have a negative CX, so CX is positive 1592.5 newtons. And the positive sign there means that all the CX's I drew are correctly oriented. So it should be going to the left on part BCD, should be going to the right on part AEC. All right, so we have that one. Forces in Y, summation of forces in Y will not immediately give me an answer, so I need to do a moment equation. Let's do moments about C. We shouldn't even have to write that, but let's write it out. Clockwise is positive, and I've got 980 newtons times 2.5 meters plus BY times 2.5 meters. Those are the only two forces that are going to create rotation about point C on that BCD free body diagram. And that just says that BY is negative 980 newtons, if we do the math for that. And the negative sign means that all the BY arrows I drew are the wrong way. So they should all be pointing down. All right. Now that I know BY, I can right, summation of forces in y equals 0. And I'm looking at the free body diagram first, so it says By minus Cy minus 980 newtons equals 0. Then I plug in the values I know. By is actually negative 980 newtons. Cy is the thing I'm solving for, so minus Cy minus 980 equals 0. So therefore Cy equals, let's see, I have two 980s that are going to get moved to the other side of the equal sign and become positive, but Cy is negative, so Cy is actually a negative 1960 newtons, and that negative sign means that all the Cy arrows I drew are opposite of what they should be. So the only thing I don't know now is AY. So I could either go to this little diagonal AEC piece and figure out AY. I think it's actually easier to go to this piece though and figure out what AY should be. So from here, now when I write summation of forces in the y direction equals 0, I have AY plus BY minus 980 newtons equals 0. And I found that BY is right here, negative 980 newtons. So AY plus negative 980 newtons minus 980 newtons equals 0. So AY equals that 1960, or 1960, yep. And it is a positive number. And I've solved for all of the unknowns on this piece. And so sometimes you have to do that. You have to work a little on the external reactions if you can. Maybe you can't even start there. And once you get stuck, you can't write any meaningful equations, or equations that they're still meaningful, but you can't solve them, is what I mean. And then you take it apart and look at individual pieces, like we did here. We only had the two pieces. And pick one of them that looks promising. Either one of these would have worked. I just like the horizontal one just because of the equations are going to be simpler to write, particularly the moment equations. And then solve as much of that one as you can. Go to one of your other pieces. In this case, we went back to the original free body diagram and solve that. So this one is, it's simple. There's only two pieces and a pulley. But there is more going on to it. This would be a medium type problem just because it would be easy to get stuck and not know what to do because you start out and you can't get all the external reactions. And you got to know what to do with the pulley. How do you take into account the 980 newtons in those ropes, or the rope that goes around the pulley. So you got to figure out that. So it's in the medium-ish level. Not terribly hard, but not super straightforward either. This guy is more on the hard side. So, and this one has a new feature that we have to talk about. So let's work on this one now and see how far we can get. The new feature, let's start with the new feature. So we've done pin, this one also does have two pins, which again can give us problems on finding our external reactions. But the new feature here is actually at C, and it's kind of hard to see, so let me make it larger. Where should I put that? Let's put it off to the side. So this is a slot. So this is an enlarged picture of this little area. So there's the piece, and inside here there's a slot. And there's a pin that moves back and forth in this slot. I guess I can write slot. Sometimes these things aren't always this orientation. Maybe you've got one that looks like this. So maybe you've got a round piece, and around this thing you've got a cylinder. We need to erase that part so you wouldn't be able to see that. This Oh, that too. There we go. This would be a slider. It would have the same type of function. These are frictionless again. So we're frictionless. In the real world, the more surface area they have contacting, then the less likely it is to have something that we can model as frictionless. So the slider might have a little bit of issues modeling as frictionless, although there are versions of this slider that have rolling elements inside of them that basically a bunch of tiny ball bearings inside there that really do make it low friction, maybe not frictionless, nothing's really frictionless, but low friction. But we model these like rollers. So it's basically like what we've been doing for a roller, where you have free movement in one direction, in this case, the direction of the slot or the direction of the rod that the slider is on, and you have constrained in the perpendicular direction. So the reactions are perpendicular to the slot, or they're perpendicular to the rod here. Sometimes you'll have just two pieces that touch one another, maybe like this. Here's one piece, and you have kind of like a roller on the end of another piece. So this is a roller, but it is possible to have these in the machine itself instead of just rolling on some kind of surface. So these are different types of connections in the mechanism itself. So ours, and our picture has the slot version. They all are doing the same thing, where you get to move in one direction, so there's no reaction in the direction you're allowed to move, and there's a reaction perpendicular to the way that you're constrained. So reactions that are perpendicular to the slot, to the rod, or to the, I don't know, the little edge there that the roller is rolling on, whatever that you want to call that. And so these things will show up every now and then, and when you do see that, you know that you can treat point C instead of treating point C like this point C where it's a pin with Cx and Cy. You can treat it as there's a single reaction at C, and you know it's perpendicular to the slot. So it gives you one less variable to work with. All right. Let's see if we can figure out what some of these forces on this piece are. We do have labeled that we do have one two-force member BE. This is a B right here. Kind of looks like a D. That's a B. So we've got one two-force member BE, and none others. Everything else is either got more than two supports, or it just doesn't meet the qualifications for a two-force member. So we've got a frictionless pulley up here. We're going to make sure that we say that this is frictionless pulley. There's a rope that goes around it. Somebody's over there pulling with 80 pounds downward, so that we know that anywhere in that cable, and those cables are supposed to be perfectly vertical, that you have 80 pounds of force. And we want to figure out what are the forces on, A, B, C, D, or one of these pieces. Let's start by drawing and I'm probably not going to draw all of these dimensions every time because there's a lot of dimensions on there. But let's start by drawing something for the whole thing so that we can see about getting some external reactions. What can we do with that? So we need to get some extra space. That's enough to start with. All right. Let's draw A, B, C, D and go from there. And then we have this little piece at B. Oh, well, at A, we have a pin, so we can put AX, AY. These are two of our external reactions. So there's A. At B, that's going to stay internal for now, so we'll leave that alone. C is somewhere right here. D is over here. ECF kind of does something like there. Oh, wrong color. E goes up through here. I missed a little bit. And then it goes over here. F is up here. So at F, we have to decide, are we going to leave the pulley on there? Maybe for now, let's leave it on. So cable connects at D and goes up around this really big pulley, kind of like that. So should be more circular, but that's fine. And we have 80 pounds here. And then at E, we do have one 2-force member connected there, but we also have this other thing, ECF, that is not a 2-force member. So we're going to have to treat E just like a regular pin that has E, X, and EY reactions. So those are our external reactions, AX, AY, EX, and EY. And then we have the 80-pound force that's causing everything to happen. Let's see, if I do moments about A, then I have two unknowns, EX and EY. If I do moments about E, I have two unknowns, AX and EY. If I do moments about B, then I have two unknowns, AY and EX. If I do forces in X, I have AX and EX. If I do forces in Y, I have AY and EY. So I don't see any equation that's going to let me start and figure out any of my external reactions. So when I get to that point, and I look for my 2-force members, which I did find one, I do have this guy, but identifying that one as a 2-force member doesn't actually help me any further on external reactions. So I need to take this thing apart. So let's look at ABCD. I like to start with the ones that are like horizontal and vertical because they're easier to deal with dimension-wise. I don't have to figure out angles and stuff. So I'm going to start with ABCD. All right, so at A, I still have AX and AY. At B, all right, so assuming that I recognize BE as a 2-force member, which it is, then I can write the force in BE. I don't have to write BX and BY. So got B right here, A there. So I'll pick this direction and call that BE or force in BE or whatever you want to call it. Also at C, remember there's a slot at C, so there's not a CX and CY, there is just C, and it's at this angle. We'll call it the force in C so that this is going to be the force in BE, so we know it's a force and not naming the member or something. Let's get back to that one. Let's do D. We'll get to that. D is 80 pounds. D is the rope going around the pulley, frictionless pulley, and coming back down, so it's just 80 pounds. Now the angle at C. So again, how this works is the member ECF has an angle theta. We'll figure out what the angle is, but right now it's just theta. Measured from horizontal. So I'm measuring angle theta from horizontal axis. So to make FC, the force, that's the reaction of this little whatever is the element roll sliding in this slot, the reaction on that element has to be perpendicular to the slot. So to make it perpendicular, I measure theta from the other axis. So remember ECF has an angle of theta from horizontal, so the reaction that's perpendicular has an angle of theta from vertical. So that's how I can ensure that it's perpendicular to the slot that it's riding in. I just got to figure out what theta is, and then I can look at some of the dimensions. Let's go back to the one that has dimensions on it. So we're talking about this angle theta, which is given to us right here, 53.13 degrees. I could also get it from the dimensions. There's a little 3, 4, 5 triangle in there that I could use to calculate theta. And there's enough dimensions on the entire truss to figure out what theta should be. So in this case, it's just given 53.13 degrees is the angle of member ECF. So that means that if I take that same angle, but measure, well, that's not going to work, measure from the vertical axis, that'll make FC perpendicular to member ECF. So that's the easiest way to think about it, for me anyway, as far as getting something perpendicular to a slot. Same thing if it's perpendicular to a rod or perpendicular to this little ledge that the roller's riding on or whatever. Just take the slot or the rod, find its angle from horizontal, for instance, and then the reaction is going to be the same angle from vertical, and that will make them perpendicular. So as long as I do that, this piece only has 3 unknowns. No, it doesn't. It has 4. It has 4 unknowns. 1, 2, 3, 4. But I can actually solve for some of them. Maybe. Let's see. Maybe I can't. Nope. I don't think I can. If I do y, there's 3 unknowns in y. If I do x, there's 2 unknowns in x. If I do summation of moments about anything, I want to have at least 2 unknown variables in that. So that's useful, but it doesn't help me. All right, let's draw the other piece, ECF. Let's see, C is going to be kind of over here somewhere, and then F is over here. All right, at F, I have 80 pounds. So F, I could choose to draw the pulley again and put 80 pounds on either side of the pulley, or I can do the same thing I did down here and just take those 2 cable forces and put them right at the pin. In this case, you know, they're gonna add into 160 pounds because you're gonna have 80 pounds right on top of another 80 pounds. Basically 2 80-pound forces going down at F. So I'll just lump them into a single 160-pound force. At C, I've already drawn the force at C on member ABD, so I have to use the same magnitude, FC is what I called it, but I have to use the opposite direction. So I have to point it this way. So there's FC, and I will need to measure it 53 degrees from vertical because it hadn't changed direction. It's just, or it hadn't changed the angle direction, it's just changed the direction that the arrow is pointing. And then down here at E, I have 2 things going on. I have EX and EY, those are the pin that is bolted to the floor with reactions. So I have them going this way. And then I've got BE itself. So I have drawn BE in tension. On member ABD, I drew it in tension. So I need to draw a tension arrow here on, what is it, ECF. I need to label that. So kind of if we put BE in here. Well, actually, this one's weird because it's not really pointing, it looks like it's pointing towards the member, but it's not really because it's pointing across the thing. So this one, let's draw the member. Let's assume the member is in tension and then we'll fix it. So let's move this down a little bit. All right, so there's the member BE. Let's draw it in tension. And what that does here is this arrow is correct, but it needs to go, oops, I want to maybe do this. There we go. It needs to go this way. Well, no, it doesn't. Get off of there. It needs to go this way. So let's get rid of that. since it's not really you can't really, put in the force at B doesn't put it in tension or compression, right? It actually makes the rod ABD bend, which is something we're not ready for yet. So drawing it on BD or BE, it's clear that it's in tension. And then at joint B or pin B, whatever you want to call it, maybe I want to call it joint, but at pin B, then I can have the opposite reaction, same magnitude, opposite reaction. So I can't really look at ABD and tell if force BE is a tensile or compressive force, because it's not really either one. It's a bending, it's causing bending. So once we get to beams and bending, which is next week, I think, that force BE on member ABD will make more sense. Right now, we know about tension and compression as an axial force. In member BE, there I've drawn it in tension, and now I can draw the reaction at E needs to go up. So sometimes you have to make sure that all three members, all three members are consistent with one another, and that might mean rearranging the way you created the forces. I could have put BE in compression, I guess, and that would have kind of helped, but this way I think is clearer, where we choose what BE is, and then we base our reactions on ABD and ECF based on what we drew here. Now, we've got all three free body diagrams. We could draw the pulley also, but that's not going to give us any information. And let's see if we have anything that is useful. So we already, BE just tells us that BE equals BE, so that doesn't help. We already looked at ABD, and we couldn't see a way to solve for anything there. So now we've drawn ECF. We have 4 unknowns, but 3 of them are at E. So EX, EY, and the force in BE are all at E. So if we do moments about E, all 3 of those will disappear in that equation, because they all have lines of actions that intersect point E and don't create rotation about that point. So that seems like where we need to start. So let's take member ECF, let's get some space in our document. Oh, not that way. I think I was on this. All right. And for member ECF, let's write summation of moments about point E. We'll choose clockwise, positive. They need to add to 0. We need some dimensions on here to do this. So we've got from E to C, there are 3 feet in the horizontal direction. So that's 3 feet. From C to F, there's a total of also 3 feet. And do we have any of the vertical ones? We know that from C to F in the vertical direction, there's 4. So from here to here, there's 4. And from E to C, there's 4 feet. All right. And that's enough for what we need. All right. So we're writing moments about E. We have 160. I didn't put my units. These are pounds. 160 pounds has a total distance of 6 feet from E to F. And then I've got FC, this reaction force on the slot, and it's at an angle. So I need to break it into FCX and FCY. So it's 2 components that I can deal with that. I guess I could try and figure out, perpendicular distance. That actually wouldn't be, well, no, it's not necessarily perpendicular to that EC. No, it is. So this is, let's do that. So this one We know that FC is perpendicular to ECF because we made it that way. The slot is in ECF, and we intentionally said that the reaction is perpendicular to that slot. So if I drew, maybe if I zoom in and draw a little slot, you know, there's a little slot in here, or a groove or whatever, that pin at C is sliding back and forth in, and the reaction FC, kind of looks like I drew as an E there, FC is perpendicular, so there's a right angle there. So in this case, I could go in, particularly since this is a 3, 4, 5 triangle, right? This is 3, 4, and so this distance is 5. I could just go in and say that the moment created by FC is FC times 5. So I could write, and it's going clockwise the way I drew it, so I could write plus FC times 5 feet. So 5 feet is, you know, this distance based on a 3, 4, 5 right triangle. You could certainly do the X and Y components and do their individual, you know, FCY is the cosine of theta times FC and the moment arm of 3 feet, and FCX is the sine of theta times FC and a moment arm of 4 feet. So you can certainly do it that way. But since you know that 5 feet is the perpendicular distance between point E and the line of action for FC, then you can just do FC times 5 feet and save yourself a little bit of calculating stuff. The perpendicular distance is always the shortest distance, right? Mm-mm. Are you asking like if part ECF could move around somehow?
Like if FC is continuing to come down, would there be a short distance somewhere?
Oh, like the line of action goes down? No, it would always, I mean, the right angle is the shortest distance. I don't know a way to like prove that, but it is that. Like you can graphically think of it here, and it's like with this green dotted line, I could never draw a different line from E out to it at any point that is shorter than the one that's labeled as 5 there. But I don't know how to prove that. I don't know how to prove that. So it is the shortest distance though. And if you're ever in doubt about, well, can I do that or not? You can always do the X and Y components, and they will. The only issue is that it, you know, puts one more term in your equation that you might have a mistake in, but you can always do X and Y components of forces at angles and deal with it that way. But in this case, I know that I defined FC to be perpendicular to member ECF. So in this case, I can do this. So I'd have 160 times 6. I would have 960 foot-pounds plus FC times 5 feet. Those have to add to 0. Therefore, FC is 960 divided by 5, 192 pounds. And then once I know that, then everything else opens up, because now I can either, depending on what I'm trying to solve for in the problem, I can either go back to ABD and only have 3 unknowns. That was actually probably easier to work with. Or I could keep working on member ECF and there's only 3 unknowns, FBE, EX, and EY. So once I know that one piece of information, then the rest of the problem is just a matter of picking one of these free body diagrams, writing your 3 equilibrium equations, and working it out from there. For instance, let's go over to ABD for a while. Let's copy this guy. Copy. And make a little room.
So should FC be negative?
Oh, you know, I didn't look at that. Let's see. Yes, it should be negative. based on my equation. Those are both clockwise moments, the way I drew them. So one of them would have to be a counterclockwise moment, which the FC one would create. So yes, FC is actually going the wrong way, the way I drew it. Oh, I didn't want this to turn that way. There we go. All right. Now on this piece, I know that FC is negative 192 pounds. I'm going to leave it in this orientation, at least the arrow, and just keep track of the negative sign. It is totally up to you. I would recommend, if you do like redrawing the arrows, then make sure you redraw all of them on all your free body diagrams. To me, that's harder to keep track of. In this case, there's only 2 instances of FC, but sometimes it can get you forget to change one of the orientations somewhere on a free body diagram that you don't plan on using, and then you end up using it, and then it creates problems. This is cleaner for me to do, is to draw everything up front and always reference those orientations when you write your equation, and then go plug in the numbers. But whatever is best for you is fine. Once I know this 192 or negative 192, then I could maybe let's do forces in X. Summation of forces in X. I only have the 2 unknowns, or well, 1 unknown now. And my equation, based on the free body diagram, would say AX minus FC times the sine of 53.13 degrees has to add to 0. Then I go plug in AX minus FC is actually a negative 192 pounds. And I can solve for AX. So 192 times sine of 53.13, 153.6 pounds. And that sine is also negative, right? So anywhere I drew AX is backwards. I only drew it this one place, but it is actually going the other direction. Then I would need to do a moment equation. So let's write one of those. Oops. So if I do, I don't know, moments about A would probably be good. According to my, I guess I need some dimensions. From A to B is, no, they're all 3 feet. Well, no, that one's not. All right, so A to B is 3 feet. B to C, that I didn't put on here, is 3 feet. And then I believe C to D is 2 feet. Yeah, 2 feet. Okay. So I was writing moments about A. So FBE times 3 feet. FC has the 2 components. This time I probably do need to use the components. The line of action for FC is this way. So if I were to do the shortest distance, it's actually out here somewhere, right? I don't want to worry with trying to figure out what that distance is. So I'm just going to use FC as FCX and FCY, and I only need the FCY component. The X component of FC line of action goes through point A, so I don't need it in this equation. So FCY is going to, the way I drew it, again, I'm not looking at the number, I'm looking at the arrow, is a counterclockwise moment, so minus FC, I need the Y component, so cosine of 53.13 degrees, it has a moment arm of 6 feet. And then, like I said, the X component does not create a moment about point A. The 80 pounds does, though, and it creates a counterclockwise moment, so negative 80 pounds, and it has an 8-foot distance between point D and point A, basically. Now I go plug in values that I know. I don't know BE, so FBE times 3 feet minus, and FC is the negative 192. So minus a negative 192 pounds times cosine to get the Y component times its moment arm of 6 feet minus 80 pounds times its moment arm of 88 feet. That's from the cable. Those all have to add to 0. And the only unknown in there is BE. So let's do some of these in pieces before I forget them. 192 times cosine 53.13 times 6. So this term, FBE times 3, this is plus because of the double negatives, 691.2, this is foot-pounds, minus 80 times 8, 640 foot-pounds, equals 0. So 691.2 minus 640 is 50, whoa, I wrote that wrong. 691.2 minus 640, 51. That's a positive, so it goes to the other side. FBE times 3 equals negative 51.2 foot-pounds. That's 3 feet there. I've left that off. So therefore, FBE is equal to negative 51 divided by 3. Whoops, 3. 17.1 pounds. And the negative sign means that it really was, I drew it in tension. Remember up here, I drew BE in tension. So it's actually a compressive member, and all of those BE arrows, all 4 of them, are drawn the wrong way. They should be going the other way. Yeah.
Where did you get the 160 from? The beginning of the 160?
Oh, the 160 on member ECF is actually this. It's actually 2 80-pound forces on top of one another, because it's the rope on both sides of the pulley. They're both pulling down with 80 pounds. And so I just added them together. They're just on top of one another, so I added them together instead of drawing them like that. At that point, you could keep going. You could get AY. You could go figure out, we never did figure out EX or EY, so you could start going back even to this diagram and getting EX and EY. Or you get AX, AY, EX, and EY from there, because I think we found AX, didn't we? Yeah, we did AX. So there's multiple directions you could take once you start finding that. The first thing in our case was finding FC. You can't find FC unless you recognize how to deal with the slot. If you put CX and CY and not FC right here, then you're going to have too many unknowns. You'll never have one of these that you'll be able to do. If you did CX and CY on this member ECF, then our moment equation would have both of those CX and CYs in it, and you'd have an unknown equation that you couldn't solve. You'd have too many unknowns in it. You might eventually be able to set up enough independent equations that you could solve them all simultaneously, but that'd be kind of a lot of work that may or may not pan out in the end, depending on if you were able to keep track of all of these equations and write independent equations. On the independent equations, in general, as long as you write only one moment equation, X and Y, for each one of your free body diagrams, they should all remain independent. But if you ever have to write 2 moment equations on your single free body diagram, that's okay, but it means that you can't write both X and Y also on there, because you'll have something that's redundant. So you could potentially set up those 2, ABD, ECF, write all their equations, maybe even throw some equations in from the entire system into a giant set of simultaneous equations and get the same answers all at once. On an exam, that's probably not going to be the way, well, it's not probably, it won't be the way that I intend for you to solve the problem. And actually something this level is probably a little bit beyond what an exam would ask you to do. if this was a hard problem on an exam, I would probably ask you to maybe, let's see, a hard version of this would be to find the value of BE, which is where we got to. That would be a really hard one though. Probably a reasonable exam problem would just be to find the force on the slot, you know, the force at that C, that 192 pounds. That would probably be reasonable. Still, it'd be one of the harder problems on the exam though, just because of the time it takes to get there. This one I think I've asked on an exam before, or something very similar to it, so this one certainly is exam type. There are plenty of web work problems like these that will give you some practice. Yay. So I think that's probably all we need to work on today. Oops, I want to do that the opposite way. I think we have enough